how to measure the association between random variables. And that is a topic which, if I had given this lecture a few years ago, I would have said that, okay, this is all material from, up to the 1920s or 1930s. But in fact, some interesting developments have taken place in those last 5 years. And I will start, of course, with the classical stuff and then go on to introduce some of these more recent concepts. Then I will talk about the normal distribution, which you all know. However, I will talk about some tricks that I think you haven't seen before. So new ways of using them to understand what's in your data. And finally, I want to use the normal distribution as part of a generative classifier, exploiting what we've learned about statistical decision theory last time. So there's a program for today, and we start by ways of measuring association between random variables. So as a reminder, the variance we had seen last time, the variance of a random variable is defined as expectation with respect to x of and this concept can now be generalized if you're looking at more than one random variable. You then look at the covariance So you look at the deviation of x from its expectation, and at this you multiply this with the deviation of y from its expectation. And altogether, this covariance describes the linear and only the linear association between random variables. So, in other words, when would we get out a positive covariance? If if we have, we can estimate this empirically, and if we have some observations in this quadrant, and let's say the expectation of x is 0 and the expectation of y is 0, then we multiply a positive number with a positive number, so we have a positive contribution. And actually here we multiply a negative number with a negative number, so we also get a positive contribution. So this would be, what I'm plotting here would be a data set which has positive covariance, and on the other hand, this kind of data here would have negative covariance. And then there are all kinds of data sets that clearly have some structure, which unfortunately does not show up. And I'll show you a few examples in a minute. However, I first want to write down how this transforms. So there is, by the way, a different way of writing this, which is sometimes useful computationally. So we can multiply out this whole thing. And we can now apply this expectation operator to each of the terms in turn. And the first one gives us the, well, it stays unchanged. The second term, the expectation of y, the expectation of y with respect to y is just a constant. So we can pull this out of the expectation operator. So I could write this as minus the expectation of y times the expectation of x. So this operator here was with respect to both x and y, but since there is no y in this function, I can simply ignore this y here, and here the argument goes the other way around. So I have minus expectation of x times the expectation of y. And this thing here, this is a constant times a constant, so it does not get changed by the expectation operator any longer. I can simply copy this. Okay, now we have minus this term, plus the same term, so I can simplify a little. And that is interesting computationally, because if you look at the first formula, it requires 2 passes through your data set. You need a first pass to compute the expectation with respect and to y, and you then afterwards estimate that. Whereas down here, you can do that in a single pass. So you can agglomerate your estimator for this quantity at the same time that you agglomerate your estimate here, requiring just a single pass through your data. And since access to hard disk is the slowest process on your computer, that can sometimes be relevant. Okay, and the other thing is, which takes a bit of getting used to, is understanding here what is still a random variable and what is already a constant, so where the expectation operator still applies to, and where or which quantities can simply be pulled out and in front of the operator. Okay. Then let's look at how these things transform. So if I have the covariance of a linear combination of random variables with weighting coefficients ai and bi, then by looking at the definition, and you will see that you can write this as follows. The variance, these are just the diagonal elements of the covariance. And with this rule that we've just seen, the variance of a sum of random variables could be rewritten as follows. I'm using a different index the second time to avoid confusion here. And now using the formula that we've just seen. And using the formula from the last slide, or this entire matrix I can decompose into the diagonal and the off-diagonal terms. And the important statement here is that overall the variance of a sum of random variables is not the same thing as the sum of the variances. If there is non-zero correlation between the random variables, and the difference is just this term here. Now, if you have multivariate random variables, you can use matrix notation. So let's say we are looking at a random variable which lives in a p-dimensional space. And in this case, if I write the covariance of this random vector, what I mean is the following. So X is a column vector, and I take the outer product of the vector and its transpose. Okay, so the first term here has dimension p by 1, and the second term has 1 by p. So overall, this is a p by p matrix. And if we now look at a multivariate random variable which is transformed by a linear operator A, so A is a q by p matrix, and X was my p by 1 random vector, I simply use the definition. And you see that I have on the left side I multiply with A's, and from the right side I multiply with A transposed. So I can pull these out. And obtain the expression for the covariance that I had seen before. There you go. So far I've been arguing with the expectation operator, which deals with, or which operates on random variables. But in real data, in real life, we typically just have a finite number of observations, so we want to estimate these quantities empirically. Sorry. So the empirical estimate of the covariance matrix is simply called the sample covariance matrix. People use different letters. I'm here using Q. X bar is the empirical mean of my sample. And xi is again a column random vector. Now, you are perhaps surprised by having 1 over n minus 1 as a normalization here and not 1 over n. And you've probably heard before that this has something to do with the bias. I want to give you a hand-waving argument for why you use that. So let's say that I know the true mean of my sample is 0. And I now have a couple of observations drawn from some distribution, and I use these few observations to estimate the spread of my distribution. Now, if I use not the true mean but the estimated mean here would be, in this specific example, a little more to the left. Because the mean was estimated from the same sample, it is better centered in the middle of the sample, and it hence looks as if the data had a smaller spread. So I'm writing that the estimated mean sees a smaller spread of the data as compared to the exact mean. By the way, we're ordering a different computer which will allow us to show you higher resolution video. So maybe we'll have it next week, and then you can hopefully see better what I'm writing. So the red thing says estimated mean sees a smaller spread. Okay. Now there are two exceptions to this rule. So you should use 1 over n instead of, in the following cases, either when the mean is known rather than estimated, or when the samples are known to come from a Gaussian distribution. Because using 1 over n for the Gaussian distribution gives you the maximum likelihood estimator of the covariance matrix. Now, obviously, all these considerations only matter if n is very small. And if n is very small, you anyway should be suspicious of your results. Once n is sufficiently large, that will not make a big difference. Okay, so that was the sample covariance matrix. And that is almost the same thing as the scatter matrix. It is the same up to normalization. So the scatter matrix, often abbreviated with S, is the same thing without the normalization. It's n minus 1 times q, sorry. Now, we often like to use matrix notation for two reasons. On the one hand, it sometimes later on in life, it makes for more elegant expressions. And on the other hand, that's closer to the code that we want to write in languages like MATLAB. So we can ask if it's possible to express the same thing, the scatter matrix, just in terms of matrices. Yes, it's possible if we use the so-called centering matrix. And so there's another bit of terminology, but a nice matrix, you will see. So this mean, so let's say X, let X be a P by N matrix comprising all observations. So I've used a capital X, but now it's no longer a random variable. It is a matrix holding all my observations. So you see the confusion with the notation already starts, because last week I've been preaching that capital letters are random variables, and now I'm using capital letters for matrix. But this is the same kind of confusion that you will have to live with if you read the literature. Yeah? So let X be this matrix, and then we can rewrite this X bar. So this is the empirical mean. So what I want to do is I want to, so let's say hopefully we have more observations than variables. That's not always the case. But here let's argue it is the case. So I can rewrite that as 1 over n times x times, if I had a computer, I would write this as a bold 1. But I don't have a computer, so you will have to figure out that this is a scalar 1 and this is a vector 1. Perhaps to help you, I could put a subscript here. And the definition of this bold 1 is that it's the vector of all 1s. So it's an n by 1 matrix of 1s. So you see what I've been doing? I've been multiplying this thing. If I just multiply this with a vector comprising all 1s, I would get for each dimension the sum over all samples. But I don't want to compute the sum, but the mean. So this is why I divide by the number of samples. Okay, so I've rewritten now my empirical mean. I have rewritten the empirical mean using matrices. Hooray! However, this is useful in a minute. Where I can write the following. So what is this thing here? I have, sorry, now I've written mu where before I wrote x bar. Excuse me. So I've taken my mean vector and I have replicated it n times. Okay, I've taken my mean vector x bar, which was just a p-dimensional vector, and by multiplying, by taking an outer product here with a vector of all 1s, I have replicated this vector a total of n times. So in summary, what I'm doing here is I'm subtracting my mean vector from each and every sample in my data set. Okay, and inserting again here the calculation for x bar. I find the following. And you see that we have x appearing twice, so I can take that as a multiplier and write the following. I is the identity matrix. And this thing here, so it's a nicely symmetric matrix, that is known as the centering matrix. So that's XCN, where the centering matrix, I'm writing it once again because you will see this further in the semester when we talk about multidimensional scaling. And the centering matrix can be used, for instance, to subtract the row and the column average in a very convenient fashion. Okay, so I can now rewrite the scattering matrix as follows. So my scattering matrix S now becomes X times Cn. This was my centered data set. So the original observations with their mean subtracted. And whenever I transpose a product of two matrices, I can write that as Cn transpose X. And because it is a symmetric matrix, I can write that as Cn Cn. And it's an idempotent matrix. So there we go. So overall, this is a way to compute the scattering matrix, and you see that it makes for a nice compact formulation. And this is why the scattering matrix is quite popular, because it allows to write compact expressions. Okay, now any questions so far? Go ahead. Is scale dependent? That is not bad per se, because it can tell us, what the spread of a random variable is. However, sometimes we're just interested in how closely are two random variables associated, and we want this measure to be independent of the units used. So let's say if I measure length in millimeter or in kilometer, and let's say weight, I want to get out a measure of association which is independent of the units. However, if I use a multiplier here, so if I multiply my length by 1,000,000 to go from millimeter to kilometer, then my covariance also changes by 1,000,000. To get rid of the scale dependence, you can normalize. And the best known type of scale independent, the best known scale independent measure is the Pearson type correlation. Pearson is often omitted because when people just say correlation, this is the one that they're talking about. This is an interesting personality, by the way. He also studied in Heidelberg, and he had a mixed bag of views. So he was in some ways quite progressive for his times, fighting for women's rights and engaging in socialism. And some say that he changed the spelling of his name to Karl with a K because of Karl Marx, but it's not confirmed. And at the same time, he was he was a fan of eugenics, so of the idea of improving the human race by weeding out, the inferior members of society and so on. And shortly before his death, he founded the Annals of Eugenics. I'm not sure if they still exist. So yeah, some of his views were quite ahead of his time, and some, well, are no longer acceptable today. Sorry? He died in 36 and was born late 1850s, I believe. But actually many of these early statisticians were quite interesting characters. I'm not sure what that says about statistics. So well, and these concepts were already partly used before him, but he was the one to officially, or to really nail it theoretically, so it's named after him. So the correlation of X and Y, sometimes just called rho. So if you talk to social scientists, they go on a lot about their rho. Yeah. So if they study something, alcoholism and school grades in religious education, and then they talk about their rho, and they want to get numbers ideally close to 1, which means there is a strong correlation. 0 means there's no correlation, and well, I cannot say it often enough, or in general, people can't say it often enough, that correlation doesn't say anything about causality. So and there are all these examples of chance correlation that you find. So we're only talking about correlation here. So you normalize by the square root of the variances. So the covariance of X and Y is normalized by the square root of variance of X times the square root of variance of Y. And because it's tedious to write, there's a shortcut, namely the shortcut is called standard deviation. So it's the covariance divided by the product of the standard deviations. And it has the following properties. Its absolute value is always smaller than 1, and the absolute value is either +1 or -1 if and only if there is linear dependence between the random variables. Of this form here. If rho is larger than 0, we say that X and Y are correlated. If it is smaller than 0, we say they are anti-correlated, which is not the same as uncorrelated, which is when rho is close to 0. And that is, of course, an interesting test, or an interesting case. So there are many statistical hypothesis tests that try to establish if a correlation is really exactly 0 or not, because if it is, that can lead to dramatic simplifications in your model. And another important notion is that of independence. Independence means that, or it's abbreviated, for example, like that, or other people prefer to write a double bar here. It means that the joint factorizes, so the joint distribution of X and Y can be exactly represented as a product of the marginals. And independence does imply 0 correlation or 0 covariance. So that works. However, the reverse is not true. Okay, here are famous examples. So in this case, there's, well, this is a Gaussian distribution, which you see in the top row. And you see here there's no clear association between the random variables. Here there's some positive correlation. And by the way, this is typically the kind of number that people in the social sciences see. So you can be really happy that you work in the natural sciences, because they would call this a respectable correlation between the two random rules. And, you know, we're typically working in this regime, and, well, this is mathematics, not statistics. Yeah? So here, one function is exactly a linear, or one random variable is exactly a linear combination of the other. By the way, the slope does not matter, so that's what's shown in the second line. So no matter if y equals x, or y equals 1/2 or 1/3 of x, the correlation in these cases is always exactly 1. Or it's always exactly -1 if the line has a negative slope. And down here are cases, you can now look at each one in turn and think about whether it is actually, whether the two random variables are independent. So take a vote. How many of these distributions are independent, or the random variables are independent? So now you need to figure out for each one, do you think that the density, which is only implicitly represented through this random sample here, could this density, if you think of it as a matrix, would it have a rank 1? Or could you represent this matrix as an outer product of two profiles, or out of two marginal densities? So who thinks that none of them are independent? I'm not going to ask mean questions. I just want to. I'm just doing statistics across the classroom. 0. Okay. 1. 1 independent distribution. 2. More than 2. Okay. So my. All right. Now, I see just one set of random variables that's independent. So I was assuming here that x and y are really the horizontal and orthogonal axes. So for example, if I rotated this cube such that it was aligned with x and y axes, then that would be a factorizable distribution. But this thing, for instance, you simply cannot, or I mean, you can try. You can put this kind of thing in a matrix, this kind of density, and then do a decomposition and look at your most important vector. So you would do a singular value decomposition. But anyway, if you put this into a matrix and compute the singular values, you will see that none of these are decomposable except for this one here. So the guy down there, you know, you can think of one marginal density that has a bump here and a bump here, and the second marginal density which is a bump here and a bump there. And if you multiply them, you get out these 4 bumps. So that works. But as soon as you started deleting, let's say, 1 or 2 diagonals of these bumps, it would no longer be they would no longer be independent. Then the circle can also not be represented, and so on. I promise not to ask mean questions, yeah. But in the break, convince yourself of that, or prove me wrong. Okay, another example. This is known as Enscomb's quartet, and another picture stolen from Wikipedia here. These 4 data sets, if you fit a straight line to them, in all 4 cases the line will have the same slope, and you will have the same correlation coefficient for all of them. And you know, here you would say, yes, this straight line is a reasonable model for that data. but that's clearly not true here. So here you would like to fit something quadratic. Here you just have, you know, clustered or noisy data plus an outlier. And same here, huh? one outlying point. So you would rather tend to fit a straight line with a lower slope here. So bottom line is that this correlation, it really strictly only tells you something about linear association between random variables. And as soon as the association is nonlinear, this will no longer help you. Let's do one analytic example here. Or counterexample to this above statement. So let's say we look at the following situation. Where x can only take 3 different values. And y is a deterministic function of x. So y is simply x squared. So there can be no talking about y being independent of x. Yeah? It is a direct deterministic function of x. However, the expectation of x is 0, and the expectation of x times y, if we insert the definition of y here, is the same as expectation of x to the third, is also 0, and the covariance by this formula that we'd seen on the first slide can be computed as follows. And expectation of y is not 0, but the expectation of x is 0. And this guy here is 0 by the previous line. So overall, we get a covariance of 0, even though we have this deterministic dependence between the two random variables. Any questions so far? Okay, so far this was all the standard stuff that you see in the normal textbooks, even in the 60-year-old ones. After the break, I'm going to show you 2 more slides of that, and then we suddenly jump to 2007.